Come on. Okay, so as I was saying, just make sure that you call ahead so that you can properly schedule for your test. Now, as far as what the test will cover, the test is going to cover chapters 1 through 4. I have the PowerPoints here in Canvas, so you can make reference to that. Chapters 1 through 4. All right, so basically the introductory stuff and scientific method, we're going to talk about that, or you'll be tested on that. Measurements and calculations, so things like sig figs and decimal places when you're rounding off appropriately, things like units and how you convert from one unit to the other, stuff like that will be covered for chapter 2. And for chapter 3, matter and the change on the go. So therefore we're talking about, the definition of matter, the difference between compounds and elements and mixtures, homogeneous and heterogeneous, and also the difference between physical and chemical changes, physical and chemical properties, stuff like that. And then chapter 4 deals with element, atoms, and ions, and those related topics. Let me just do a quick look at that PowerPoint here. Download this. Okay, in the meantime, let me check this out. Okay, so this person is asking, Taryn is asking, how many tests are we having for this class? You're right, you'll be given 3 tests, but I'll be dropping the lowest score, the lowest test score. So I'll be averaging the 2 highest scores. All right, so that's an answer to Taryn's question. And then Alexandria is asking, may you repeat the information for the test scheduling? I was having trouble. Oh, okay. So I was saying that the test will be given from September 27th to October 1st. So it won't be next week, it will be the other week, all right? And the test must be done in the testing center. And I didn't say this, but I'm going to say it now. You can go to any one of the testing centers. So if it just so happened that the testing center in, let's say, Citrus is nearest to you, then you can go there. You don't have to come to the one at Ocala if the one at Citrus or Levy is more convenient for you to go to. All right. Make sure that you call ahead and make an appointment, because they have their rules about when you can actually do the test, because you need 1 hour to do the test. And if you go there at 6:30 when the center closes at 7, for example, then they won't give you any more time to complete the test. And I think that's all I said in terms of the scheduling. One thing I never said, or I didn't say, is that you need to make sure that you complete the test in ink, blue or black ink, all right? And you're going to need your calculator. And I will provide, or the testing center will provide, the packet, the same packet that I've posted in Canvas. You will have access to that, so you don't need to bring your own copy, all right? That will be provided for you. And they will also provide for you an extra sheet of scratch paper. What else? I think that's pretty much it. Let me see, somebody's asking a question. Elijah is asking, is the testing center open on weekends? As far as I know, no. In fact, let me check here. Let me see here. I just looked at the webpage for the testing center, and I guess I closed it. Let me scroll down here. Hold on, let me see here. Academics. Okay, where did I find it? Testing. Okay, testing and assessment. Okay, so let's see. Okay, according to this, at the Ocala campus, it's open Monday through Thursday, 8 a.m. to 6:30 p.m. and Friday, 8 a.m. to 4:30. So it's not open on Saturdays. I'm sorry. Unfortunately, it's not. If you want me to tell you what the times are, at the Ocala campus, it's 8 a.m. to 6:30 p.m. Monday through Thursday. And then on Friday from 8 a.m. to 4:30 p.m. Those are the times that the testing center at the Ocala campus is open. The Citrus campus is open from 8 a.m. to 4:30 p.m. And the Levy campus is open. Oh, by the way, I'm sorry. Citrus campus, Monday through Friday, 8 a.m. to 4:30 p.m. And the same hours for the Levy campus. All right, so those are the times. All right, so I hope that answers your question. Okay, Mr. Jackson. Now, Miss Gomez or Mrs. Gomez is asking, what if the only time we can take it is during this class? Usually my previous teachers would give us the week off. Well, very interesting question. I don't think I've ever had that situation before, but if that's the case, then I guess you'd have to take the test at the time that you can. And if that means that you have to miss my class, then no worries, because as usual, I will record the lecture and therefore you can go to YouTube or go to, of course, I'm going to post the video in my module section on the Canvas page for this course. So you can go there to basically catch up on what you may have missed. So that's basically the only solution I can offer to answer that question, Miss Elisa Gomez. Okay, any other questions? So will you give the testing center the test packets? And when we sign in, whenever we schedule, will they give us the packet? If you're talking about the packet, which includes the tables, you know, like the periodic tables and conversion factors and so on, yes, those will be provided for you as well, in addition to the test. So you do not bring your own copy, all right? So I hope that answers your question, Taryn Stepinski. Okay, any other questions? And by the way, as I said before, today's class is pretty much a review, which means that if you have any questions, I mean, not only about the testing center and all that, but any questions on the topics themselves that the test will cover, then now would be a good time for you to ask those questions, right? So that you'll be prepared for that test. So any questions concerning the test or those topics? Oh, can we bring our own copy? No, you cannot. Okay, so somebody, who is it? Oh, Taryn again. Okay, Taryn was asking, can we bring our own copies of the tables? Answer is no, because that will be provided for you. And that is true, even if they have nothing written on them, right? So the same tables that are posted in Canvas is basically what you'll be provided. So that's why I insist that you don't bring your own. Okay, any other questions? Any other questions? Well, if there are no other questions, what I'm going to do is proceed, hold on, with continuing this course. Let me close this. And we're going to talk about chemical composition, because I think we're finished with chapter 7. So, okay, so in chapter 7, what we're looking at is chemical composition of compounds. And in this topic, what we're concerned with, as the term seemed to suggest, is the makeup percentage-wise, and in particular by mass, of a compound. So if you have two substances or two elements making up a compound, then we're looking at the percentage of each element. So just to give you a simple example, in the case of water, hold on, did I introduce this to you guys? Hold on, I have a sneaking suspicion I covered this. Did I talk about the mole? Anybody can tell me? Yes, okay, so where did I stop the last time? Can somebody remind me? because I think I remember talking about the atomic mass. Hold on, let me see here. Okay, did I do this example? Okay, somebody said yes. And I think I did these examples. Did I talk about molar mass? Oh, I did. Wow. I must have covered a lot. Okay, so let me see here. Did I talk about
I think we might have finished this chapter.
Oh, okay, cool. All right. If we finish this chapter, I don't remember finishing it. That's the thing. Okay, let me check something here because I wasn't prepared to teach this today because I thought that you guys might have questions. Let me check something here. So if we finish that, that means the next topic, let me publish this just to be sure. So I guess the next topic is, okay, what's going on here? Publish, update. Okay, so the next topic would be stoichiometry. So let me open this up and download. And let me check one more thing here before I start teaching it. So let me go assignments. Okay. Assignments. Okay, all right. So let me, or I'll talk about that later. Let me commence with a discussion of stoichiometry. So basically, what we'll be talking about in this chapter are situations where we look at the quantitative relationships between substances involved in a chemical reaction. And here is where you're going to see the importance of knowing how to balance an equation, because balancing an equation is very important when it comes to these calculations. So you're going to see that clearly in this section. Another thing that is also very important in this section is the whole mole concept, because what you're going to see is that the balanced equation gives you a mole-to-mole relationship between the substances involved in a reaction. So we need to review a couple of things from the previous chapter. The first thing is that the molar mass of an atom is basically the atomic mass expressed in grams per mole. And you need to remember also that 1 mole is equal to this number, which is Avogadro's number, right? So basically the molar mass will contain this number of atoms for the particular element, right? Which is equal to 1 mole, all right? And then when it comes to a compound, the molar mass will be equal to the sum of all the molar masses of all its atoms according to the formula that's given. So here's the relationship between the molar mass, the moles of the element, and the grams of a monatomic element. And here's the relationship between the molar mass and the mass of a substance. It could be an element, it could be a compound, whatever, divided by the number of moles of that substance, all right? So we can establish also a relationship between the number of moles, the number of molecules, and Avogadro's number based on this equation right here, all right? So the number of moles would be equal to the number of molecules divided by Avogadro's number for that particular compound, molecular compound. Okay, so we have the relationship established between the numerical value of the molar mass, the mole, and the number of particles. And it's true for any type of particles, be them atoms, molecules, formula units, ions, electrons, whatever, all right? So what we're going to look at are calculations which looks at these relationships between mole mass and volume, all right? So the first step in this process, whenever you're doing these types of problems, is that you need to determine the chemical equation, and that equation must be balanced, right? It makes no sense that you proceed with the rest of solving that problem without starting off with a balanced equation. And that's the reason why we talked about balancing equations in the previous chapter, all right? So if you're given this, you have to ensure that this is balanced. And I think we did this already. To balance this equation, we have to put a coefficient of 2 here and a coefficient of 2 here in front of the iron, all right? And therefore, once we get that, then we can proceed to the rest of solving the problem. Now, the reason why we need to have a balanced equation is because of this statement right here. The coefficient in front of the formula represents the number of moles of the reactant or product. So basically, what this is telling you is that for every 2 moles of aluminum that reacts, 1 mole of iron 3 oxide will react with it to produce 2 moles of iron and 1 mole of aluminum oxide. So that's the reason why we need to have the balanced equation, because we need to get the correct coefficients so that we can use them to do whatever problem solving we need to perform. All right, so as stated here, there's a 2:1 to 2:1 ratio, mole ratio between the aluminum, the iron 3 oxide, the iron, and the aluminum oxide. Okay, so let me talk about introduction to stoichiometry. And as I said before, stoichiometry is that area in chemistry that deals with the quantitative relationships that exist between reactants and products in a chemical reaction. And fundamental to stoichiometry or solving stoichiometric type problems is the establishment of the mole ratio, which is the ratio between the moles of any 2 substances that are involved in a chemical reaction. So these 2 substances could be products or could be reactants. And of course, the mole ratio would have to be obtained by looking at the coefficients in the balanced equation. So this again underscores the importance of having a balanced equation to begin with. In some problems, they might give you a description of the reaction in words, and therefore you have to translate that description into a balanced equation. And therefore from there, you can go on to do the rest of the stoichiometric problem. So let us look at a couple of examples. So we have this reaction here, the reaction between nitrogen and hydrogen to form ammonia. As you can see, this equation is balanced, right? And based on the coefficients for each of the substances involved, we can establish the mole relationship between the nitrogen, the hydrogen, and the ammonia, which is a 1:3:2 relationship respectively, all right? So we can write down a conversion factor or fraction, which represents the mole ratio between any of these 2 substances. So for example, between the hydrogen and the nitrogen, or conversely, the nitrogen and the hydrogen, it's a 1 mole of nitrogen divided by 3 moles of hydrogen, all right? So we see where the mole values come from. It comes from the coefficients, all right? Or we could look at the ratio between the hydrogen and the ammonia. In this case, it's a 3:2 mole ratio, all right? So that's where those numbers come from. They come from the coefficients in the balanced equation, all right? So that's important, the mole ratio, because it is used to convert the number of moles of one substance into the corresponding number of moles of another substance in a typical stoichiometric type problem, all right? And the mole ratio is basically used in every type of stoichiometric problem. So I think I made this point earlier. The mole ratio is basically fundamental for solving these problems. And the only way to get the correct mole ratio is to start off with a balanced equation. If the balanced equation, or if the equation is not balanced, then more than likely your answer is going to be wrong because you'll be operating based on an incorrect mole ratio, all right? So what we're going to look at is how do we use the mole ratio method to do calculations of this type. So you could be given a question and you could be given the equation, or you could be given information based on which you're going to get or derive the balanced equation. And you're given some numbers. So, numbers representing the amount of substances. So the first step is that you convert the quantity of the starting substance to moles. So for example, if you're given the amount in grams, then you'd have to convert to moles. And we know how to do that based on what we have done in the previous chapter. Now, that is if it is not already given in moles, because in some cases, the question might be generous enough to give you the mole value already, which you don't need to calculate. So if you're given a mass in grams, then you need to convert it to moles in order for you to move to the next step, right? And the next step is that you convert the moles of the starting substance to the moles of the desired substance using the mole ratio from the balanced equation. So this is important. This is the reason why the balanced equation is important, because it gives you the mole ratio. And you can use that mole ratio to convert the moles of the starting substance to the moles of the desired substance. And then step number 3, if required, you need to convert the moles of the desired substance to the units specified in the problem. So you might be asked to get the mass of the other desired substance, in which case, once you get the moles from step 2, then you convert that moles into grams. And therefore, that's how you'd solve a problem of that type. So that's basically what is involved. These 3 steps are fundamentally what is involved in a typical problem-solving effort to deal with stoichiometric problem. So again, we're going to go into these steps into more detail. So again, the first step is that you determine the number of moles of a substance. And of course, the way you do that is that you multiply the mass in grams by this conversion factor, 1 mole divided by the molar mass, right? And that gives you the moles. So that may be necessary in some cases, such as in this case right here. You're given a mass of sodium chloride, which is 292.215 grams. And you're given a molar mass, which you could have well determined yourself, but whoever wrote this question is generous to do that for you. And the question is asking how many moles of sodium chloride are present in that grams of sodium chloride. So let me set up my pen here. So the way you'd set this up is that you start off with the 292.215 grams, and you multiply that by 1 mole divided by 58.433 grams. And let me do the number crunching here, 292.215 divided by 58.433. And according to my calculations, when this is rounded off to 5 sig figs, 5 sig figs. Yes, 5 sig figs. This works out to be equal to 5.0009 moles. All right, so that's basically how you convert from grams to moles. If you're given a question, a stoichiometric type problem where you need to do that, all right? So, and this is something, of course, we all should be familiar with. Okay, so the next step, step number 2, is that you determine the mole ratio of the desired substance to the starting substance. And of course, that mole ratio is obtained from the coefficients of the different substances in the balanced equation. So the mole ratio would be, that you would use would be equal to the moles of the desired substance in the equation. Go back to my pointer. Okay, whoops, why is this? Okay, so the moles of the desired substance divided by the moles of the starting substance in the equation. That is the mole ratio that you would use to convert from the moles of the starting substance to the moles of the desired substance, all right? And then we multiply the moles of the starting substance by the mole ratio to get the moles of the desired substance. So this is the setup for that. You start off with the moles of the starting substance, you multiply by the appropriate mole ratio, where you have the moles of the starting substance down here as the denominator, the moles of the desired substance in the equation. So this part here you get from the coefficients, and that will give you the moles of the desired substance. So that's basically how you do that. And I think the next slide is an example of that. So in this question here, they gave you the balanced equation, luckily, and it says how many moles of lead-2 chloride will be formed if 5.000 moles of sodium chloride react. So in this case, let me write down what is given. I'm sorry. So let me go back to my pen. And let me, in fact, hold on. Let me choose black. I think black is more visible. Okay, so you're going to start off with what is given, which is 5.000 moles of NaCl. And the question is asking for the moles of lead-2 chloride. All right. So what I would do is that I'll start off with the 5.000 moles of NaCl, and I will multiply that by the conversion factor, which represents the mole relationship between the lead-2 chloride and the sodium chloride. And as you can see from the equation, there is a 2-to-1 ratio between the two. So I would put 1 mole of PbCl2 above as a numerator, and down here I'd put 2 moles of NaCl as a denominator. So this goes with that, and I don't think I need to do this on the calculator. The answer is going to be 2.500 moles of PbCl2. Oops. And that would be the answer for this question. All right. Okay, are there any questions about this particular example? Any questions? Okay, so, all right. Okay, so let's continue. The third step, of course, is, and this is only if required, because sometimes questions don't require this. Whatever you get as the mole value in step 2, then if required, you may convert it to the equivalent mass value. All right. So if the answer is to be moles, then you don't need to do anything else. But if you need to convert to grams, let's say, then you need to multiply the mole value by the appropriate conversion factor. All right. So for example, if you want to calculate grams, and we all know how to do this, let me go back to my pointer here. So if you want to convert to grams, then you multiply the mole value by the molar mass, and that's it. So if you want to convert 5.00 moles of water to grams, you multiply by this here, which represents the molar mass, and that will give you the mass in grams. All right. If you want to determine the number of atoms, then you multiply the moles by Avogadro's number, right? So for example, if you want to convert 5.00 moles of sodium to sodium atoms, then this is what you multiply by to get the number of sodium atoms. So it all depends on what you're asked for. If you want to get the number of molecules, again, you multiply the mole value by Avogadro's number to get that. And an example is shown here, all right? Okay, so that's basically an overview of the steps that you take to solve a typical stoichiometry problem. So let's look at an example where we're converting from, let me see this here. We're converting from moles to moles. Now, I'm going to skip this here. This is just giving you some general information about phosphoric acid and how it's made. But the important thing is that we're going to use this equation right here. And fortunately for us, this equation is already balanced, so we don't need to balance it, all right? So the question here is asking for you to calculate the number of moles of phosphoric acid formed by the reaction of 10.00 moles of sulfuric acid. So they gave us a balanced equation here. And let me just write down the information that is provided. Let me go here. Okay, so you're given, and write it here, you're given 10.00 moles of H2SO4. And the question is asking for the equivalent value in moles of phosphoric acid produced. All right. So what I would do is start off with the 10.00 moles of H2SO4. And then I would multiply that by the mole ratio between the sulfuric acid and the phosphoric acid. That's a 3-to-5 mole ratio. So I'm going to put 5 moles of H2SO4 down here and 3 moles of H3PO4 above. And when you work this out, this is going to give you 6 point, okay, how many sig figs? Oh, this should be 10.0. So let me take out that 0 here, which means that the final answer will be recorded to 3 sig figs, which will be 6.00 moles of H3PO4. All right. So that's basically how that is done. All right. Any questions about this example? Any questions? Any questions? Okay, so let's move on now to another type of stoichiometric type problem, but this time we'll be looking at how we do mole to mass calculations, or vice versa, mass to mole. So basically you're given, let's say, the mole of one substance, and you're asked to determine the mass of another substance involved in a reaction based on the balanced equation. All right, so the object of this type of problem is to calculate the mass of one substance that reacts with or is produced from a given moles of another substance involved in a chemical reaction, right? Now, if the mass of the starting substance is given, then we need to convert it to moles, and we all know how to do that. And then we go on to use the mole ratio to convert from the moles of the starting substance to the moles of the desired substance, and then we change the moles of the desired substance to mass of the desired substance if the question asks for that. All right, so here's an example using the same equation that we used before. The question says, calculate the number of moles of sulfuric acid necessary to yield 784 grams of H3PO4. So we start off with 784 grams of H3PO4, and you're asked to determine the moles of H2SO4. All right, so this is what we're given, and this is what we're trying to find. All right, so the first step in this process is I'd write down the 784 grams of H3PO4, and then what I would do is convert it to moles. All right, so let me do this, where I'm going to have 1 mole of H3PO4, and down here I would have the molar mass. So what I'm going to do is, now the molar mass, of course, you can calculate, but I'm going to cheat a bit. I'm going to use my molar mass calculator. Okay, so the formula is H3PO4. And according to my molar mass calculator, the molar mass of H3PO4 is 98.00 grams of H3PO4. All right. So by doing this, we would have converted the grams of phosphoric acid to moles. All right. So the next step is I would look at the mole ratio between, again, the phosphoric acid and the sulfuric acid, the same factor 3 mole ratio. In this case, I'm going to put 3 moles of H3PO4 down here. I'm sorry, H3PO4 down here. And up here, I'm going to put 1 mole of H2SO4. No, I'm sorry, not 1. 5 moles. What am I thinking? 5 moles of H2SO4. All right. So this will go with that. And basically what we'll be left with is our answer expressed in moles of H2SO4, which is what the question is asking for. So we have to do some number crunching here. 784 divided by 98.00 times 5 divided by 3. Okay, let me do this again. I think I made a mistake. 784 divided by 98.00 times 5 divided by 3. Okay, so that's correct. So the answer I got, and folks, feel free to redo these calculations and let me know if I'm doing something wrong. But based on my calculation here, the answer is 13.3 moles. All right. So that's basically how I would do that problem. Any questions? Any questions about this particular example? Any questions? Okay, moving along. So let's look at another example. Now, in this case, they gave us the moles of, well, they gave us a balanced equation, and they gave us the moles of one reactant, or I should say the product, because there's only one product. And they are asking for the mass in grams of one of the reactants. All right, so like I always do, I'm going to start off with writing down what is given, 12.0 moles of NH3, and what is required, which is the grams of H2. So this is a bit of a reverse of what we did before, because what we did before, we started off with the mass in grams of one substance, and then we tried to find the moles of the other substance. So this is the opposite. You're given the moles of one substance, and you're asked to find the mass in grams of the other substance. So I'm going to start off with the 12.0 moles of ammonia, and then I'm going to write down a conversion factor, which represents the mole ratio between the two. So down here, I'm going to put, according to the equation, there are 2 moles of ammonia for every 3 moles of hydrogen. So I'm going to put 2 moles of NH3 down here as a denominator. And above as a numerator, I'm going to put 3 moles of H2. So that goes with that. And then the next step is where I would convert the moles of hydrogen to grams. So that means I'm going to need a molar mass. And for hydrogen, the molar mass, you can look it up on your, in the periodic table. There are 2 atoms per molecule. So the molar mass is 2.01 grams of H2. So this will cancel out with that. So your final unit would be grams of H2. So again, we have to do some calculations here. 12.0 times 3 divided by 2 times 2.016. And according to my calculations, when rounded off to 3 sig figs, the answer becomes 36.3. So let me write that down here. 36.3 grams of hydrogen. All right. So that's basically how that is done. Okay, any questions about this particular example? Any questions? Okay, so let's look at another type of stoichiometric type problems where you're given the mass of one substance and you're asked to determine the mass of another substance involved in the reaction. So in this case here, there's like an extra step compared to what we were doing before, where you have to convert the mass of the starting substance to moles. Then you have to convert the moles of the given starting substance to the desired substance using a mole ratio. And then finally, you convert the moles of the desired substance to the mass. That would involve the molar mass, of course, to do that. So let's look at this example using the same equation as we did in the previous problem we just looked at, but we're given some different numbers here. So in this case, you're given the mass of the hydrogen and you're asked to find the mass in grams of the ammonia. So let me write this down here. You're given 112 grams of hydrogen and you're asked to determine the mass in grams of NH3, all right? So what you would do first is that you start off with the 112 grams of hydrogen. You convert that to moles. So you're gonna have 1 mole of H2 above and then 2.016 grams of H2 below. So this would go with this. And then the next step is the mole ratio between the ammonia, the NH3, and the H2. So as we can see, there's a 2 here for the ammonia, and there is a 3 here for the hydrogen. So we can express that here as 2 moles of NH3 as a numerator, and 3 moles of H2 down here as a denominator. Then there's one more step we have to take, and that is that we have to convert from the moles of ammonia to grams of ammonia. In other words, we need to multiply by the molar mass of ammonia. So let me do my calculation here of the molar mass, and that's equal to 17.03 grams. So that goes up here, 17.03 grams of NH3. Okay, so that this cancels with this cancels with that. So you're left with your final answer expressed in grams of NH3. So let's do the calculation here. 112 divided by 2.016 times 2 divided by 3 times 17.03. And according to my calculations, rounded off to 3 sig figs, the final answer here would be 631 grams of ammonia. And that's how you do that type of problem where you're given a mass of one substance, you're given a balanced equation, and you're to determine the mass of another substance involved as either a reactant or a product. Okay, any questions about this particular example? Any questions? Any questions? Okay. Let me check the chat. Okay, there's no questions there. All right, so let's move on now. And I think this may be the final topic that we're going to cover in this chapter. And this has to do with the concept of limiting reactants and yield calculations. All right, so let's talk about limiting reactants firstly. So basically, you may have reactions which involves more than one reactant. All right, and very often in practice, what you'll find is that it's very difficult in some cases for the reaction to go to completion if we use the right stoichiometric equivalence of the reactants based on the balanced equation for the reaction. So what we have to do in order to force the reaction to take place or to produce a sufficient amount of product is that one of the reactants will be used in excess, right? Which means that the other reactant, we call that the limiting reactant, all right? That's a limiting reactant. We call it, we call it a limiting reactant because, as the term suggests, it basically limits the amount of product that you'd expect to get, right? Another thing about a limiting reactant that you need to be aware of is that a limiting reactant is the one that's completely used up in the chemical reaction. And we're going to see that at work in the examples that will be following this page, all right? So as stated here, the limiting reactants determines the amount of product that can be formed. And that's very important. Once you identify the limiting reactant, then that is used to determine how much of the product is formed. And it's also used to determine how much of the excess reactant that is used up in the reaction. All right. Now, in order for me to explain this, I'm going to use an analogy involving the construction of a bicycle. So let's say you're in the business of manufacturing bicycles, right? So in order to make one bicycle, right, one unit, you're going to need 2 wheels, you're going to need a frame, and you're going to need a pedal assembly, right? So we could use this equation here to represent what it takes to make one bicycle, right? You're going to need 2 wheels. Hold on, let me change this to my pointer here. Okay, you're going to need 2 wheels, you're going to need 1 frame, and you're going to need a pedal assembly. So that combination will give you 1 bicycle. All right, so let's say that you have 8 wheels at hand, 3 pedal assemblies, and 4 frames, all right? So the question is, how many bicycles can you get out of that combination, all right? So if you look at things from the standpoint of the wheels, right? You have a total of 8 wheels. Well, in order for you to make 1 bicycle, or, you know, in order for you to make enough bicycles to use up all these 8 wheels, you're going to need 4 pedal assemblies, right? But we only have 3, right? So therefore, you cannot use up all the wheels here in order to make as many bicycles as you can. So obviously, some of the wheels here would be in excess. If you look at the things from the standpoint of the 4 frames, then according to the equation, for 4 frames, you're going to need 4 pedal assemblies. Again, that's impossible because you have only 3 pedal assemblies. So therefore, at least one of the frames will be in excess. Now, if we look at things from the standpoint of the 3 pedal assemblies, the 3 pedal assemblies are going to need 3 frames and 6 wheels, all right, based on the equation. So what that means is that all the pedal assemblies will be used up, 6 of the wheels will be used up, and 3 of the 4 frames will be used up, which means that there'll be 2 wheels left over and 1 pedal assembly left over. And therefore, the maximum number of bicycles that you can end up with would be 3 bicycles, right? So in this context here, let me just skip all this here because I just explained all that. So in this context here, the limiting part would be the assemblies, the pedal assemblies, right? Because they're all used up. And not only that, but they determine ultimately how many bicycles you can potentially make, right? So therefore, the pedal assemblies is the limiting item and is analogous to the limiting reactants in chemical reactions, right? And then the 2 wheels and the 1 frame left over would be the excess items, which would be analogous to the excess reactants in a chemical reaction, all right? So I hope this clarifies to you the whole concept of the limiting reactant or limiting item when it comes to manufacturing bicycles in this case, but the same concept can be applied to manufacturing anything, all right? Okay, so let's look at an actual chemistry example. So let's look at this reaction here. The reaction between hydrogen and chlorine to form hydrogen chloride, right? So as we can see in this equation here, the mole ratio is given by the coefficients, of course, which is 1 to 1 to 2, right, respectively, between hydrogen chlorine and hydrogen chloride, all right? So we can use these models to represent what is happening in this chemical reaction. Now, let's say you have a situation where you have 1, 2, 3, 4, 5, 6, 7 hydrogen atoms and 1, 2, 3, 4 chlorine molecules, actually, not atoms. So these, you have 7 hydrogen molecules and you have 4 hydrogen molecules at the start of the reaction, right? Well, based on the stoichiometry of this equation here, based on the coefficients actually of this equation here, we can conclude that the chlorine would be the limiting item, which would be completely used up, right? Because each chlorine molecule will require a hydrogen molecule. So therefore, all of these chlorine molecules, the 4 of them will be used up and will react with 4 hydrogen molecules, right? So therefore, you're going to end up with, according to the balanced equation, you're going to end up with a total of 8, 1, 2, 3, 4, 5, 6, 7, 8 hydrogen chloride molecules. And therefore, what that means is that since 4 of the hydrogen molecules will be used up, then 3 of them would be left over. So these are the 3 hydrogen molecules right here, all right? So therefore, in this particular case, the chlorine would be the limiting reactant and the hydrogen would be the reactant in excess. And therefore, the chlorine, being the limiting reactant, is the reactant that determines how much or how many hydrogen molecules will be produced. And the hydrogen, of course, cannot do that and will have some excess left over, all right? So that's basically what this is demonstrating right here. So what this is showing you are the chlorine molecules, all of them being used up to produce the 8 hydrogen chloride molecules. And as a result, the hydrogens won't be all used up. As a result, you're going to have 3 molecules of hydrogen remaining, all right? Okay, so that's an actual chemistry example. And this is an explanation based on what happens at the molecular level. So let's talk about the steps that we need to take in order to determine which reactant is limiting, all right? So the first step is that we calculate the amount of products formed from each reactant. And in actual fact, come to think of it, step 1, okay, yeah, let's just say this. You don't need to calculate the grams, actually. You could just stop at calculating the moles. But you can calculate the grams if you want to. It won't affect anything. But typically when I do problems of this type, I basically calculate the moles of product formed from each reactant. And then we determine which reactant is limiting. How do we determine that? Well, it's based on the calculation that you did here. The one that produces on paper in your calculation, the one that produces the lower amount or the least amount of product, that would be the limiting reactant. And any other reactant that is present will be in excess. And then based on that fact, then we can calculate the amount of the other reactant required to react with the limiting reactant. And then we subtract that from the starting quantity of the reactant. We're going to see an example of this shortly. I just thought I should just go through this first so that you have an idea as to how we do this type of problem. So what step 3 is all about is calculating the amount of excess reactant. You use the limiting reactant to determine how much of the excess reactant that will react, and then you subtract it from the initial amount of the excess reactant. And that will give you the amount of reactant that is unreacted. All right, so let's look at those steps at work in the following example. So this question says, how many moles of HCl can be produced by reacting 4 moles of hydrogen and 3.5 moles of chlorine? And then the next question is, which compound is the limiting reactant? Okay, so this is what I would do, all right? Let me go to my pen function again. And let me start over here. So this is what I would do. I would start with the 4, shucks, let me do it again. 4.0 moles of H2. And then what I would do is, based on the 4.0 moles of H2, I would determine how many moles of HCl will be produced. So there's a 1 to 2 mole ratio between the two. So I'm going to put 2 moles of HCl down up here as a numerator, and 1 mole of H2 down here as a denominator. So that will give me 8.0 moles of HCl. And then I would do the same thing, but this time starting with a 3.5 moles of Cl2. And in this case, I would convert the moles of Cl2 to the moles of HCl by the mole ratio, 2 moles of HCl over 1 mole of Cl2. And this would equal to 7.0 moles of HCl. All right. So basically what I'll do next is compare this to this. And the answer for the first part, because the question is asking how many moles of HCl can be produced, the answer would be this one right here. 7.0 moles of HCl can be produced based on starting off with 4 moles of H2 and 3.5 moles of chlorine. Now, the next question is, which compound is the limiting reactant? And the answer is the chlorine. The chlorine is the limiting reactant. Why? Because based on the calculation that we have just performed right here, this would be the expected amount, right? And that is based on the moles of chlorine that you're starting off with, right? So the one that produces the lower amount of product based on the calculation, starting with each reactant, is the limiting reactant. So in this particular case, the chlorine would be the limiting reactant because it determines how much product you expect to get. All right? Okay, any questions about this example? Any questions? Any questions? Okay, let's move along to a more complex example. It's more complex for several reasons, not the least of which they did not give you the equation. They gave you the information based on which you can figure out what the equation is. So the question says, how many grams of silver bromide can be formed when solutions containing 50.0 grams of magnesium bromide and 100.0 grams of silver nitrate are mixed together? And then the next question is, how many grams of the excess reactant remain unreacted? Okay, so the first thing we need to do is figure out what the equation is. So this is where I'm going to turn it over to you guys. First thing we need to figure out are the reactants. So can anybody, based on the information provided, tell me what the reactants are? Well, Okay, so somebody says the magnesium bromide. Okay, you have the incorrect form name though. It's not silver 1 nitrate. It is simply, well, it's not silver 1 nitrite, it's silver nitrate. So let's write down the formulas for each of them. So Mg Br2 and Ag NO3. Okay, so those are the reactants. So what would you expect the products to be? Well, they gave you one of the products. So what are the products? Magnesium nitrate, okay, and silver bromide. So they gave you the formula for silver bromide. What's the formula for magnesium nitrate? Anybody? Very good. Mg NO3 2. And then we need to balance this equation. So how would we go about balancing this equation? Okay, place a 2 in front of the silver nitrate. I would agree with that. What else? Place a 2 in front of the silver bromide. Very good. All right. So that's what we need to do. We cannot do anything else until we do the balancing of the equation. All right. Okay. Whoops. Sorry. Sorry about that. Okay. So what we're going to do next is try to figure out how much product you expect to get, right? So they gave you 50, what's going on here? 50.0 grams of magnesium bromide. And what we're going to do is try to figure out how much of the silver bromide that can be obtained based on that. So the first step would be to convert from grams to moles. So we're going to have 1 mole of magnesium bromide above and the molar mass. So I'm going to go to my calculator again to calculate the magnesium bromide molar mass. And according to my calculator, that gives 184.11, 184.11 grams of MgBr2. And then the next step is the mole ratio between the silver bromide and the magnesium bromide. And based on the balance equation, you have 2 moles of AgBr above as a numerator and 1 mole of MgBr2 as the denominator. And then we work that out. So that would be 50 divided by 184.11 times 2. And I got 0.543 moles of silver bromide. Okay, so that is based on the 50 grams of magnesium bromide. So what I'm going to do now is start off with 100.0 grams of silver nitrate. I'll convert that to moles. So we're going to have 1 mole of AgNO3 above as a numerator. And below, I'm going to have the molar mass. So let me calculate it here. So according to my calculator, that's 169.87. 169.87 grams of AgNO3. Oops. And then the next conversion factor is the mole ratio between the silver nitrate and the silver bromide, and that's a 2-to-2 or 1-to-1. 2 moles of AgBr divided by 2 moles of AgNO3. And then you work that out. Let's see here, 100 divided by 169.87. So according to my calculations, this works out to be equal to 0.589 moles of AgBr, all right? So if you look at these two, you'll notice that this is lower than this. So therefore, this represents the moles of AgBr that you'd expect to get. So that means that to get the mass of silver bromide produced, you're going to take the moles here and multiply it by its molar mass. In other words, you're going to have 1 mole of AgBr, and above the molar mass, so let me calculate that, AgBr. Okay, according to my calculator, that gives 187.77 grams of Ag. I hate when this does that. Okay, so 0.543 multiplied by 187.77. And according to my calculations, when rounded out to 3 sig figs, the answer becomes 102 grams of silver bromide, AgBr. And that's how you do that. All right? So that answers the first part. Any questions about this? Any questions about the first part? Okay, so for the second part, it's asking for how many grams of the excess reactant unreacted, okay? So the excess reactant would be obviously the silver nitrate, because the limiting reactant is the magnesium bromide, which produces, based on the calculation here, the lower amount of silver bromide expected. So what we're going to do is start off with the 50.0 grams of magnesium bromide. So 50.0 grams of MgBr2. And what we're going to do is convert to moles like we did before. So we're going to have 1 mole of MgBr2 and the molar mass, which we had before, which is 184.11 grams. So we're going to write 184.11 grams of MgBr2 down here. Now the next mole ratio, or the next conversion factor, is going to be the mole ratio between the magnesium bromide and the silver nitrate. And if you look at the equation, let me go back to the previous page. If you look at the equation that we determined, you'll see that the mole ratio between the magnesium bromide and the silver nitrate is 1-to-2, right? So the next conversion factor is where we have one mole of MgBr2, Br2, and 2 moles of AgNO3. All right. And then the next conversion factor is where we convert the moles of AgNO3 to grams. So you're going to have 1 mole of AgNO3 down below, and up here the molar mass, which I think we have from before. Let me see. AgNO3. Do we have the molar mass of AgNO3? 169.87 grams. So up here you're going to have 169.87 grams of AgNO3. So this is going to go with that. This is going to go with that. This is going to cancel out this. and your answer will be expressed in grams of AgNO3. Okay, so let's do that number crunching. 50 divided by 184.11 times 2 times 169.87. And according to my calculations, this works out to be equal to 92. I have to round out to 3 sig figs, so this should be 92.3 grams of silver nitrate. Now, this represents the mass of silver nitrate that reacted, all right? But what the question is asking for is how much of the silver nitrate remains, right? So how do we get that? Well, we have to start off with the amount of silver nitrate that was there to begin with, which is 100.0 grams. So therefore, down here, I'm going to write down that the mass of AgNO3 remaining, will be equal to 100.0 grams minus 92.3 grams, and 100.0 minus 92.3. So according to my calculation, this works out to be equal to 7.7 grams of silver nitrate remaining. Okay, so that's a typical limiting reactant type problem, stoichiometry, limiting reactant, you know, all those concepts involved, all right? Okay, any questions about this particular example? Any questions? Any questions? Okay, I think I'm going to stop here for today. The next topic we're going to discuss is reaction yields, all right? So I'm going to just commence from there, unless if you guys have any questions concerning the upcoming test, we probably can deal with that instead of doing this. So it's all up to you whether or not we do a bit of a review or if we continue discussing this chapter. Before you leave, let me just say that I think there's something I forgot to mention in regards to the test. I think I told you that the test covers chapters 1 through 4. The corresponding assignments for those those topics covered by the test would be assignments numbers 1 through 7. All right. So if you want to look up the assignments to review them for that test, then those are the assignments. And I think I sent back to you guys, if not all of you, most of you, your graded work, and for those assignments. And in the Canvas system, I've also posted the assignment keys. I've published them. So if you look here, you see these are the folders, chapters 1, 2, 3, and 4. This is where those assignment keys, answer keys will be located, all right? So that's basically what you can use to review for your upcoming test. Okay, any questions before we leave? Any questions? Hold on 1 minute. Okay, yeah, I think that's pretty much it. I don't think there's anything else I need to say. So if there are no questions, that's pretty much it for today. And I'll see you guys next Wednesday. Until then, take care.